day, folks. Today we're going to be demonstrating the MIG welding process. So grab a seat, get comfortable. Welcome to the School of Fusion. All right, this is one of our MIG welders here. We have two of them available. And they all have the same parts. We have a nozzle and a ground. These are our electrodes. They can be found right here. So this is our ground, this is our hot. They have a nozzle. Looks like this. And it has a button. Okay. The purpose of this is when everything is hooked up, that we complete a circuit. When we pull the trigger, this gun will feed wire. And it will also feed, in our case, we use a shielding gas. And that's what this tank is at the back of the machine. It is a composite of argon and CO. That's our shielding gas. 75% argon, 25% CO. So when we push or pull the trigger, we feed the wire, and the shielding gas will also come out the nozzle. And we adjust the rate of current with this knob here. And also we can adjust the rate at which the wire is deposited out of the gun. Okay, so here we are again back at our MIG welder. If we open up the side here, now we can see where all that wire is coming from. Okay, so we have a large, in this case, 40 pounds of our wire. Now the wire must match the base material which you're welding. If you're welding steel, this is the one. If you're going to weld stainless, this spool has to be stainless. If it's aluminum, again, it must match the base. So primarily we do steel here most of the time. That's what's loaded. Now, if we come back and grab the nozzle, okay, so I'll get them both here. Now you can see when I pull the trigger, you'll see the wire feed. That's how it keeps coming out of the gun. Like so. And also, when that's happening, if we look at our shielding gas, you'll see a little ball come up dictating the amount of flow. There we go. We've got 40 pounds. Now those of you that haven't fallen asleep yet would have noticed I said 40 pounds of gas. Well, that'd be a pretty tall order, wouldn't it? What I should have said was 40 cubic feet per hour. Now, that's the rate of flow of your shielding gas. Anything more is a waste. And the reality is that's giving you quite a large margin of error, because generally you would go no more than 30. But we set it up for the students to give you a bit wider berth, but you don't need any more than 40. So, okay, as I said, we've got two machines. This is the other machine. This has got a lot more bells and whistles and electronic gizmos. So for this one, we adjust our wire feed here, and our amperage here. Now these are rheostats, so the rate is infinite, whereas with our other machine it's more of a mechanical, so it has certain set values. It's got a lot of electronic adjustments here, fine-tuning if you will. We can spot weld with it, we can set a time, we can control the run in and the burn back. Those would be adjusted by the individual based on his welding technique. And there is a two-way and a four-way stop switch. That's so that we can utilize the spot welder. Now, these are all nice. They can let you fine-tune, but really, to utilize these features, it would be someone that is welding a production type part where they're doing it for 6 hours a day, and they can tweak it or zero it in or find that sweet spot just for the way they weld. But you'd do wise just to leave those all alone, because it's more than likely it's just going to be a problematic issue. So just leave them to zero. The reality is, when you have that type of diversity, it comes with a compromise. This machine here is a purpose-built, no bells and whistles. It makes a much better weld than this one will in mild steel. Now with this one, because it has all the bells and whistles, we also have available an aluminum spool gun, which allows us pretty precise welding of aluminum, so long as it is thicker than 1/8 of an inch. Okay? Okay, the MIG welding process. It's simply a short circuit. When the machine is hooked up, ready to go, when the welder squeezes the trigger, the wire comes in contact with the base metal, creating a short circuit. This causes the base metal to melt and the wire electrode to melt. The wire burns back at a faster rate than the base metal, thus lengthening the distance the arc must travel, which causes it to stop. However, remember, we keep our finger tight on the trigger, the wire will continue to feed. And when it reaches the metal again, another short circuit happens. This process is repeated over and over until the welder has completed his weld. The short circuit happens roughly about 60 times a second. And when set correctly, you will hear that distinctive buzzing noise. That's what that is. When a machine is set up properly, some welders will say it should sound like bacon frying. Okay, let's get this procedure going. First thing we want to do is pick up our gun, pull the cap off the nozzle. There we go. Make sure that this part of the gun doesn't have splatter on it. There are small holes here which our shielding gas will get out. If it is blocked, just use a wire brush and brush it off. Okay? The nozzle portion, if there is what we call spatter in there, what you've got to do is clean it out. So all you need to do is take a pair of the MIG welding pliers, They're made like this for a reason. The funny end is made to just clean that up. Okay, there's nothing in there. We've already made sure this is clean. It is. We push it back on. We use this. This is an anti-splatter. This is an aerosol. Sometimes they're just little drums of it and you stick the tip of the nozzle in. The heat melts it. It's just a matter of giving it a little squirt. That's it. All this is the same as using an oil in a fry pan, or in the case of this being an aerosol like Pam. Any splatter that goes into the nozzle will not adhere and it simply falls out. Okay, so the next thing we need to do is we need a certain wire stick out. Right here, when we pull the trigger, the wire comes out. It may or may not be set correctly. Let's say it was here, much too long. We want about 1/4 to 3/8. 3/8 I find perfect. And actually, again, there's the MIG welding tool. It's made to give you 3/8. So simply grab the end, give it a pull, make sure it's at the end of its travel, and you have diagonal cutters. If the cutting edge is to the outside of the nozzle and you bear the tool to the nozzle like this, when you cut that off, there it is. There's your magic stick out. 3/8. Perfect. Okay? So, the next thing we need to do is when we weld, we want to make sure of the way we hold our gun. If this is our material, oops, hang in there, folks. Okay. If this is our material, you want to hold the gun at about a 10-degree angle. So there would be 0, right? You're going to rotate it 10. And in this orientation, it's going to be 0, right? Because I'm just doing a flat weld. So we're going to push our weld and hold this gun at 10 degrees. Right here, looking at the monitor, I can see I'm a little too much. I'm a good 22.5 degrees there. Right? I'm darn near 45 degrees. Way too much. Want to bring that up 10 degrees. 10 degrees is the sweet spot. Okay? Now, with MIG, probably 95% of the time, you will be pushing in the direction of your weld. That gives us a nice wide weld. It gives us fair penetration. And it allows the shielding gas to cover that molten puddle as we progress through our weld. Okay? That shielding gas will cover the molten puddle just like a blanket. Okay? That's its job, being the blanket to cover that weld while it's still hot. Okay? So when we weld, we have to maintain a height of our wire. Again, that magic number, 3/8 of a stick out. We want to keep that constant. If we're moving up and down, then our weld is going to be altered in all stages of the height difference. Okay? So It has to be steady. I always tell students, you've got two hands, use the other one. Just takes a finger, anywhere on the gun, I usually hold it like this, and that will make it rock solid. Okay? But it's a pretty tall order to hold something at the same height while traversing in another direction with just one hand. One of the downfalls of MIG welding is you're behind the gun. You want to keep the wire at the leading edge of the molten puddle as you traverse. Well, if you're welding, right there I can't see where the heck that wire is in regards to the edge of that molten puddle. I always tell students, it's a little awkward, but position your face where you can see where that wire is as you traverse. Okay? Because if you're going to the front of the puddle, to the back of the puddle, the front, the middle, the back, you're ending up with cold welds. It's not penetrating into the base. Then you rush and go into the front, you go to the back, you get a cold spot. So it's not a strong weld. When you weld material, it needs to be clean. If the material has got paint, oil, coolant, you've got to wipe it off. It will vaporize, but the problem is that shielding gas. If that is vaporizing off, it's creating quite a turbulence. That shielding gas is no longer able to cover that molten puddle and protect it while it solidifies. You end up with porosity, and that's nothing more than the perforations on the toilet paper. That's where it breaks. Catastrophic weld failure. Okay? So if it's had any of those substances, just give it a wipe with a clean cloth. Now, most of the material that will weld is hot rolled steel. So whenever we form steel hot, it develops an oxide. Okay? If we want our weld to be as strong as the host, we need to grind that off. We don't have to grind the whole thing off, just where we're going to do our weld. Because the mill scale will not vaporize. It simply falls into the weld like, I don't know, the crumbs at the bottom of the chip bag. So when it solidifies, it's not the same composition or solid throughout. Okay, so again, that's where your weld would fail. Now, if the weld doesn't matter, it's just a temporary weld or something, yeah, you could stitch it. But if this was going to be subject to vibration, if you were welding this onto a piece of equipment and you didn't clean off the mill scale and there was any type of movement or vibration even, it may be in very short order that you're observing cracks in that weld. And that's because you didn't clean off the mill scale. Okay? I'm not going to bother for this demo. There's no need. But we do have disc grinders there that make quick work of it. Okay? So we've covered the angle, the direction of travel. Now the amperage. That's another thing. Okay. Now I've used this machine a long time. So when I go to set my amperage, it's already in the back of my head. That's 3/16 I have, mild steel. I know that I'm going to put it on the high. And I know number 3 is going to work just fine. And my wire feed is 50. Now, again, I know that if I'm going to do some really light material, say a 1/16 of an inch, I know that I would take out my electrode, my positive, and I would put it down into the low range. And I would turn my adjustment knob to the 2, and I would slow my wire feed down to about 20. Okay? That's because I've done it for some time. Now when you come up to a MIG welder, you've never used it before, all MIG welders will have a starting point to help you get into the ballpark. You might not get into the infield, but at least it'll get you into the park. Okay, so there's a chart, and it will have the recommended places to start. So if I look, let's see, I said 3/16. So I look up here, and it tells me my material size. Okay, so it's saying high, number 2. Now I said I use number 3. Remember, these are starting points. And then for the wire feed, they're recommending, if my wire is 35 thou, they're recommending my feed rate would be set at 45. Okay? Now, that's a little bit different than what I am using. Not much, just a hair more. I'm just using just a hair more heat and just a hair more wire feed. But you have to fine tune it to your particular welding finesse. Whether you're a fast welder, whether you move like a tortoise, or whether you move like a hare. You've got to tweak it to your style. Okay? And this has got a listing for 3 different wire feeds, or wire diameters. We can run 24, sometimes it comes as 23 to 25, but basically 24 thou, 30 thou, and 35 thou. And they have a listing there for 45. Now that's a pretty heavy wire. Well, you'd have to go full throttle. You'd have to give it everything you could in regards to amperage and wire feed. Okay, so as I said, if you were doing 45 thou wire, you'd have to go full throttle. Now, welding machines are based on what we call duty cycle. So this is a 200 amp. That's the most amperage that I can deliver. They give a duty cycle of 40%. So what that means is if I'm going full throttle, 200 amps, in 1 minute, I can only run that for 20 seconds and the machine will stop to cool. Okay? So that's one thing to bear in mind. If you have to run your machine full throttle, sometimes it's a little better if you can find a machine with a higher rating, because its duty cycle will allow you a little bit longer. This machine is rated at 256 amps. And again, a 40% duty cycle. So now, if I'm running what I was on this one, maximum 200, and I'm running 200 there, I'll be able to squeeze out almost 30 seconds continuous welding before it shuts off. Okay? Okay, we've got some examples here of improper welding, and we're going to identify them and come up with a solution. Okay, so the first piece, if we have a look here, this first piece, I look at this weld and I can see porosity, what we call porosity. You can see the little holes, the little voids there. That tells me one of two things. Either our nozzle on our gun is plugged, or else the tank is empty. So, the first thing we want to do is take our nozzle cover off and make sure that there's no obstruction in the nozzle. If that's not the case, walk over to the tank, take a look at the pressure gauge for the total tank, and then see if it still has gas in it. If it does have gas in it, try depressing the trigger on the nozzle and just make sure that the indicator moves, showing that gas is being delivered. If that's the case, then there's a blockage somewhere in the whip. That's between where the gas is injected and the nozzle where the arc occurs. Okay. Number two. Okay, I look at this and I can see that this is what we call ropey. You can see it just looks like a rope. Okay? That tells me one thing. Not enough amperage, not enough heat. I can qualify that with the fact that there's no splatter around it. It's just a wet piece of rope. So in this case, I'd bump up the heat. Try again. This one is thin and ropey, like our last one. But if you look carefully, you can see quite a bit of spatter all along the side of the weld. Okay, it's thin, it's ropey. What that tells me is that the amperage and wire speed may in fact have been correct. However, the welder has traversed way too fast. Way too fast. So what I would do with this one is I would try slowing my feed rate and see what happens then. That's all it's going to take in this particular sample. Now here we're looking at a weld like we want to see. Okay? The width of the weld is about twice the height. Okay? So that's what we want. There's a little bit of spatter, not much, just a little. And when I turn the piece over, I can see that the heat penetrated right through the host material. So I've got good penetration, I've got good weld form. I would continue on my weldment using where the welder is right now. This one, it's starting to widen out. The height isn't really changing, the distance from the host to the top. It's not really changing, but the width is. This is just a little too much heat, just a little. So you could bump it down just one notch and try again. This one, way too much heat. Look at how wide that profile of that weld is. It's darn near flat in relation to the height of the weld. This was very hot. And as a matter of fact, on the bottom, we can see where it's actually cratered right through the host, which we don't want to have. A little tiny pimple every now and again, that's the absolute max, but this is quite significant. Way too much heat. So on this one, I look at that and I know I'm way too hot and it's quite excessive. I'm going to slow it down, maybe 2 adjustments, and take another pass. What I recommend to students is, if you're doing a weldment, it's a one piece. Do yourself a favor, grab a scrap piece of metal, similar size, and just use that to get your settings just right, rather than start on your weldment and have to grind it or re-prep it. Okay, it'll save you a lot of grief. Now, we've just been doing simple flat welds here. Just a flat weld. So what I showed you, or what I've done here to show you, this is what we call a butt weld. We've joined 2 pieces of metal together right where they meet, or the butt where they meet. Now I welded a small 45-degree weld chamfer on both pieces, butt them together, and with the welder set at the proper heat settings, I run my pass right down the center. If I do all those things, then this piece should be the same as if it was one solid piece. I should be able to bend this 180 degrees right on top of the weld, and it shouldn't fracture. If it does fracture, then it was welded incorrectly. Okay? I may try that and we'll see what happens. So that's a butt weld. Now this is a T-weld. When we do a T-weld, we've got 90-degree bisecting materials. So we still hold our torch at a 10-degree lead-in angle, but now on the other axis, we're going to hold it at 45, so that we put the wire right down the root, or the center, where these 2 pieces meet. And our weld, see if we can see it here. We should almost appear to have a 45-degree fillet, which we do. Alright, so there's a couple simple welds that you may end up doing. Okay, there are some hazards in welding that we need to take a look at. Radiation burns. Because the arc is developing a high-intensity ultraviolet light, our skin and our eyes would be subject to radiation burns. So the first thing is our eyes. Now, we have some helmets here that will shade our eyes so that we don't receive a burn. Now, they have adjustments on them. So you have to make sure before you strike your arc that the helmet is set correctly. This helmet here, it has a knob on the side, and this is what I use to adjust my shade that will be activated when I strike my arc. It goes from 9 until 13. Now generally, 11 is a very safe spot to start at. if you're welding steel that's 3/16 to 1/4 inch, it's going to require a certain amperage to melt that host material and your wire. That's our amperage setting. So if we're welding correctly, 3/16 to 1/4, then a number 11 shade will protect our eyes from burn. Okay. Now, if we were welding something very heavy steel, maybe a thicker wire, let's say, for example, 1/2 inch. That's pretty thick, but you'll get the idea. If we were welding 1/2 inch, that machine would be set full throttle. Give her everything we got, full 200 amps, and the radiation would be much greater because of the intensity in the arc. Okay? So in that case, if I was welding something that thick, that hot, I would bump my shade right up to 13, and that would give me enough protection. If I was welding something that was very thin, let's say a 32nd of an inch to a 1/16 of an inch, then I might turn this down to 9, maybe 10, so that I could protect my eyes yet still see the wire in the molten puddle. It's kind of a trade-off. You have to be able to see that wire in the molten puddle. Now, my eyes are green, so I would probably try that at 9. But if your eyes are blue, you're more susceptible to getting a burn in the eye. I would try that particular thickness at a 10. And if I could still see the wire in the puddle, I would continue on there. Okay. Now, there's also some other settings on the helmet. They're generally on the inside. There's 2 little knobs in here, and they are for intensity and delay. Okay? So those are kind of to tweak the helmet settings, the speed at which it darkens based on my welding environment. Let's say, for example, I'm welding and I've got a bright light coming in. We've got a window over here. So if I'm welding early in the morning, I may find that just by moving my head ever so slightly, I'm getting enough light to change the shade. And I'm not ready, I'm not in position, or I'm still trying to look at where I'm going to weld. In that case, I could adjust the delay or the setting for sensitivity to kind of tweak that in. All right, so it's kind of it's a little finesse to get exactly what you want. But you're always safe to start midsection. Okay, and then you can make an adjustment if you deem it necessary. But the important one is make darn sure that that's set at the shade you require. You're responsible for it, no one else. Now, my helmet, and you have one helmet over here that is the same. It's the same style of helmet. I can turn this knob back to a position called grind. Now that's only a number 3 shade, a brazing shade. If I was brazing, I could wear this helmet on grind, and it would protect my eyes enough from the ultraviolet light from an acetylene and oxygen flame. Okay? So you sure don't want to start welding set on grind. It's up to you. Make sure. It's your eyes. Okay. Our skin, like I said, radiation burns. We've got leather jackets. They're over here. Okay. Make sure you put them on. If you had some nylon somewhere, that you're wearing nylon and you are welding, The danger with that is it will melt and bond to your skin. Very painful burn. So some people will weld in the warmer weather wearing just a cotton jacket, and that's fine. Cotton is great, okay? But never, ever, ever, under any circumstances, wear an old ratty old jacket that's made out of nylon as your welding jacket. We supply leather jackets, so make sure you put them on. An important part about the jacket, do the collar up. I see so many welders with burnt necks, okay? The first two buttons are your most important as far as I'm concerned. So many people weld open like this, and this is where they get their radiation burn, right there, okay? So do those up. Now, you also need gloves, okay? These jackets are long sleeve, so once you put on your welding glove, you get full coverage, okay? Now, the welding gloves are also on the bench by the helmets, so everything you need is there. Oops. Often, I get a question, do I have to wear safety glasses? I'm wearing the helmet. Well, the simple answer is yes. Unless you walk around with your helmet down all the time, you're going to be flipping it up all the time to look at your weld, reposition your part, whatever. If it's up and you're not wearing safety glasses and something comes flying through the air, maybe someone's chipping something with a hammer, who knows? Wear the safety glasses underneath, okay? I think that just about covers it for the safety. Make sure when you're welding, you're not near any combustibles. You don't want to be welding on the table and have a bunch of wood piled up. You don't want to have a bunch of oily rags, well, rags period, any combustibles, right? Put them on the bench, put them away from the action, because you're going to have a starburst of sparks, and that can cause a fire. Okay? Be aware of what people are doing around you. You have to shield so that no one in the area gets a welding flash. So it's up to you to position the welding curtains. We have some curtains here. Here's another one. Okay. These are portable. They're movable. So before you start to weld, take a look around and figure where you have to put those guards. Okay, because we don't want anyone walking through the shop suddenly getting a welding flash. Make sure they're in place. So that's your basic safety rules. There are hazards. Do what's necessary, and it'll be a safe operation. Okay, there's a couple other things in safety that I may not have covered. Number one, make sure your legs are covered. Okay, you don't want to be welding with shorts. It's pretty foolhardy. You're either going to get an arc burn, radiation burn, or you're going to get a serious third-degree burn. Okay, so make sure your legs are covered. And again, no nylon. Also, be aware where your legs are standing or your feet are in proximity to what you're welding. There is a lot of molten splatter when you weld, so you don't want your feet directly under that splatter as it cascades down off your part, off the table, and onto your foot. Okay? And if you are grinding your fabrication as you weld it, always think where your sparks are going from your grinder. Never haphazardly just start grinding without paying attention of who's around your surroundings. Make sure you direct that grinder so that it fires the sparks in a safe direction.